Well, we're going to look at some problems using integration by use substitution. And again, the basic idea behind that is that we're trying to change these complex integration problems. We're going to try to rewrite them in terms of one of our basic antiderivative rules. So as a general principle, whenever we have something that's exponential, we want to let u be the exponent. This works out as long as the derivative of u is within the expression there. So so let's try this one. So we're first going to say, all right, well, let's let u be cosine x. Well, if u is cosine x, that means the derivative of u with respect to x is going to be negative sine x. And if we were to solve for du algebraically, we get this. And the idea behind this problem is, why do we want to solve for du? Well, once we substitute for u in there, we can only have u's. We can't have anything else. So the problem says, all right, we can put du in there if we have a negative sine x dx. So we don't have a negative, but what we can do is force the problem to have a negative sine x in there. So whenever we're dealing with some constants, we're allowed to do that. So if I put a negative here, now I can't just change the problem. It has to be equivalent. So if I multiply a negative times a negative, I get a positive. And then once we have that, we have everything that we need to set up this problem. So I'll underline right here the negative sine x, and then the dx is over here. And those are going to go away and become du. And then we also have right here, this is the same thing as u. So I could rewrite the problem as negative the integral of e to the u du. And so again, u substitution just basically changes these complex problems into just a general antiderivative rule that we know. And then so based off that, we solve that negative. The antiderivative of e to the u is e to the u plus c. And then we just put c back, or put u back in there. So it's e, u is cosine x plus c. And again, we could check our work by taking the derivative of this, and that would be the chain rule, and you would see that we'd actually get the integrand of this integral. All right, so for the second example, we'll do the same thing. So the exponent is going to be u, and if that's u, then du dx is going to be 4x to the third. And then if we solve for du, because we want everything in terms of u, we get this. Okay, so we need in the problem there to be a 4x to the third dx. Now this problem doesn't have that, so we got to change that somehow. So one thing we can do is, first we're going to pull out that constant 6. Okay, so our problem says we have to have a dx, we got that. We have to have an x to the third. We also need to have a 4, so we'll put a 4 right there. Now we can't just multiply anything by 4 and it being equivalent unless we also do the inverse operation there. So if we multiply by 4 and divide by 4, we're over okay. So everything that I've underlined here, I'll even box there, that becomes du. And so if I were to rewrite that problem now, 6 over 4 is 3/2. The things in the box there become du. And then we have e, and then instead of this, we're going to put the exponent there, and that is the same thing as u. And again, all we did is we changed this problem now into one of our basic antiderivative rules. So e to the u becomes e to the u, and I'll put u back in there. U is x to the fourth plus 2, and then plus a constant. All right, so that's reviewing, just going over exponential functions. We can do something similar when we're talking about trig. So generally with trig, this is a general rule. Whatever we're taking the cosine of or sine of, for example, that's what it's going to be u. So let's try this first problem. So u is going to be 2x plus pi. And so the derivative of that, du dx, equals 2. So that means du equals 2 dx. So our problem needs a 2 dx. We have a dx. We don't have a 2, so we're going to put a 2 there, and then we're going to also change that to a 1/2 so that they are equivalent. So let me rewrite that problem. And again, the reason why we're doing this is that we have a rule for trig ratios that is taking the antiderivative trig ratios, but it's all single variable. So once we have something else, cosine of something more than a single variable, we have to change the problem. All right, so the 2x, so I'll underline those. Those are both become du. So the next step here is we have 1/2. So that 2 and dx are gone, and they become du. Cosine stays there. And right here we say u, all this is u. And then we have a rule for that. So we just need to think, okay, what can I take the derivative of to get cosine? And that is sine of u. And we'll put u back in there. And plus c. And again, we could double check that by taking the derivative of this whole thing, and that should work out. All right, one more example with some trig. So again, the thing that we're taking the sine of is generally what u is. It's not always, but generally that's a good rule to follow. So we'll guess and check. So there's u. So du dx is 4x to the first. So du equals 4x dx. Now, there's a few different ways of getting 4x dx, but I think it's easiest for many students just to pull out that 8 and deal with that later. So I'll have the x sine of 2x squared pi dx. Okay, so for us to get a 4x dx, we need a 4 here. So I'll put that there, so 4x dx, and then we'll also divide by 4. So that 4x dx, that goes away, and that becomes du. Oops. Erase that. So that du, we have sine of this part right here becomes u du. And then we just have to think, all right, what do we take the derivative of to get sine of u? And that is going to be negative cosine. So negative 2 cosine of 2x squared plus pi, and then plus c. And again, you could double check that by taking the derivative, and we're going to use the chain rule to do that. And maybe let's just look at one more example. I'll do that on the next page. And this one is a little bit of a trick here. Let me actually scroll down to the very bottom. Here we go. This one right here, we don't have an antiderivative rule for tangent x. So we're going to have to change this problem, and we'll do that by using a trig identity. So sine over cosine. Cosine x is the same thing as tangent. And so this is kind of a unique problem. I guess I'll put a star by that. For us to do this, we're going to say u is cosine x. So du dx, the derivative of that is sine of x. And then if we put the dx over here, you'll notice that's sitting right there. So that thing I just circled becomes du, and on the bottom we have 1 over u du. So this problem is actually a little bit more similar to what we did yesterday. The antiderivative of 1 over u is the ln of the absolute value of u, and that is cosine x plus c. And there's our last problem. So this last one again is a little bit unique review of a trig problem. It's more what we did yesterday. I hope that helps.